Welcome back, everybody. In my last video, I went over the effects of the length of a surface on the tolerance and the way that that tolerance is applied to the surface. And I'll just go over that quickly, just a quick recap, but I'll link the video below as well. So we were talking about how if we have two plates and we were putting fasteners with some nuts on it, the angularity of the faces relative to the stud or the screw has an effect on the fatigue. And the claim that I made in that video is that having an entire surface that's controlled to, let's say a parallelism, this is the number we came up in the last video, and you can go look at how we came up with that, but the parallelism of 0.873 to datum A across the entire plate is different and better than if we had that same tolerance applied to, let's say, some counter bores in the plate. And the reason for that is just some simple trig, and this is not the example we went over, but this is just a simple way to represent it. If you have a shorter surface and a some sort of tolerance zone, let's say, and I picked 2, it has a different angle of the surface, this angle relative to this, than a much longer surface, even though the tolerance zone is the same. And the claim, I suppose, was that this is a much better way to control that because the length of the surface is longer, so you're going to have a smaller angle. But there's something dangerous in controlling a surface this way. If you're aiming to keep the angle below a certain number of degrees or radians or whatever system you're using, for the purpose of keeping a joint aligned to the datums, let's say, controlling the surface, the entire surface, in that way is a little bit dangerous, and I'll show you why. In this scenario, we're saying that this nut is going to be located somewhere around here, and there's another nut that's going to be located somewhere around here, and the surface, the parallel surface up here, has to be within this 0.873 millimeter tolerance zone. And what the implication was in my last video was that if you do it this way, you are going to end up with some sort of surface like this that ends up having, the angle that you want. I believe we were aiming for 1 degree, or maybe it was half a degree. I don't quite remember, but it's going to have some angle that you desire. But the problem with this is this assumes that the error is going to come, the error relative to the datum A surface is going to be some consistent plane. So in this case, the parallelism is 0.873, but this is a perfectly flat plane, so the flatness would be 0. But that's just not the case, and that's, while that might be the most likely scenario of what we would get, it's not the only scenario or the only situation you might have with this type of call out, because a parallelism, like I said in the last video, is not controlling some degree. And what that means is that you could have a situation like this, where you have a really bad local parallelism, as well as some areas of the surface that are nearly perfectly parallel to the datum. So the flatness as well as the parallelism is 0.873. And you might say, well, this is unlikely, but if a quality department measured this surface and had this result, this part would pass. So if you're now sitting there going, well, what the hell am I supposed to do? Because this is no good. We can't call out the entire surface. parallel to the datum, because you might have some sort of local lack of parallelism, and this is no good because the parallelism of these counterbores is too much. So what am I supposed to do? Well, there's a couple things. So number one, the parallelism here will result in a nasty angle because we didn't redo the math. We just pulled this tolerance and put it onto the counterbore. So if we had gone back and said, done the math on these counterbores to get our parallelism to the datum A surface to be under, 1 degree or half a degree or whatever we were aiming for, this would be a perfectly fine solution. But then the second question, I suppose, is, okay, well, I can't put counterbores on my part. What am I supposed to do? And there is a way to deal with that, where you have a plane like this and you want to control a smaller area, and I'll show you what that looks like. So what we can do, and there's no direct example of this in the standard, but figure 1-13 in the 2009 standard has a paragraph associated with it called limited length or area indications. So what we can do is we can draw a chain line around these holes, and we need to shade in the region. And it's unclear, how large this shaded area is, so we do need to give it a size tolerance. So we'll say 20 millimeters, and this is a minimum. That's implicit, but we can be explicit with it and write minimum. And this is quite powerful, because what we can do is we can put a parallelism tolerance and say 4 times parallel to something relative to A. And then underneath, we can say within shaded area or region, or whatever language you want to use. And this is quite powerful, because what we've done is we've said in each of these shaded areas, and we should probably, be explicit and say this 20 millimeter area is centered on the bolt hole. So you could apply a true position to it, or you could just say centered on each individual hole. But within these shaded areas, we can have a specific parallelism tolerance relative to A, and we would do our math to figure out what that parallelism tolerance needs to be to keep our joint face angularity below the 1 degree or the half a degree that we want. But then we can apply, a much more loose tolerance. Let's say, 2 millimeters relative to A to the whole surface. So what we've done now is we've controlled the entire surface to this 2 millimeters parallel relative to A, but then within these specific areas, we've controlled it to ensure that our joint faces, or our joints, will be reliable. So we've created a much cheaper part, potentially, because at some point there might be a part where, this is the area with the bolt, let's say, and maybe the region in the middle ends up with some crazy deviation that would not be acceptable, within this 0.873. But because this region is outside of our shaded areas, maybe it's below this 2 millimeter parallelism tolerance, and we could accept the part because it would work. So this is actually quite powerful. So the conclusion of this video is that if you want to accept parts that are going to be functional and reject parts that will not be functional, you don't want to, or you want to avoid in trying to indirectly control areas of a face, or indirectly controlling features, and you want to make sure you directly control as many features as you can. And it does, add a little bit to the drawing and may potentially make it more complicated, but in a high production environment, something like this could save parts. Anyways, like and subscribe if you found this useful, Have a good one.